The webinar today is on geomembranes that don't like to sustain tension and what's the implication for BGMs. It is presented by Professor Kerry Rowe and Eric Blond, and the webinar is sponsored by Colotage. So ACIGS is, I think most of you guys know, it has 44 chapters, probably 45 now. I think there's a new chapters that came out. We have about 4,000 members globally, including corporate, individual, and students. For you that doesn't know, ACIGS actually has a website which has a great collection of our previous webinars. So if you have any topic that you would like to listen to, just log on to our website and search the webinar library. And if you need a certificate, just send an email to us and we will send a certificate of attendance. So little promotions on the next coming conference, GeoAsia in Brisbane next year. It's coming up in June. And if you are interested in geosynthetics, I would highly recommend you to grab the early bird discount that is still available. So two speakers today is Dr. Kerry Rowe and Eric Blond. And I'll do a very quick introduction. So Dr. Kerry Rowe grew up in New South Wales and obtained 2 undergraduate degrees and 2 doctorates from the University of Sydney. So he worked for the Federal Department of Construction for 8 years before immigrating to Canada. So he's currently the Barrington Bachelor Distinguished Professor at Queen's University in Kingston, Canada. He's also the past president for ACIGS, and he has published extensive papers on barrier systems, and also that's dealing with bituminous membrane, amongst others, and been consultants for about 150 projects. While Eric Blond is an independent consultant and registered professional engineer in Quebec and Alberta, so he provides technical service to the geosynthetics and building materials industries. He is actively involved in several technical committees and associations. He is the chairman for STMD 35 subcommittees on membranes. He is also a chairman of the Canadian committees of ISO TC 221, IGS Council, and also the chair for IGS Technical Committee for Hydraulics, and etc. So Eric has authored over 100 technical papers in conferences and courses. He's a lecturer in I don't know what's the pronunciation. Hopefully I pronounce it correctly. Polytechnique de Montreal. So that's all from me, and I will pass it to our webinar sponsors, which is Colotage. Thank you, Colotage, for sponsoring this webinar, and I'll pass it to Rob. Rob, all yours.
Thank you, Sue. Just let me check. We are on here. Is that showing now?
You are showing the other screen, Rob.
Sorry.
That's the screen with your PowerPoint.
You just need to change it to presentation mode, Rob.
Oh, okay. Here we go. Here we go. Thank you.
Yep. All good.
All good. Thank you. Thank you very much, Sue, for that introduction and for arranging this webinar. And also a big thank you to Professor Kerry Rowe and Eric Blond for your time and your presentations. As ACIGS Australia, it's always our pleasure to sponsor an event incorporating bituminous geomembranes. And as I say, we're also proud to be a platinum member of ACIGS. I'm going to do a quick 5-minute introduction here, and I'm just to show you some of the very large projects of BGMs that are used around the world and have been for more than 30 years. There's a lot of laboratory as well as real-world testing that's been completed. We also like to think that we have a culture of continuous improvement and development. So these types of webinars, even though there's some tough items discussed here, we like to see that as learning, and we'll keep on improving on that. So thank you very much to the two presenters for your time. As we say, if we focus on the good gets better. So thank you to the two presenters. Now, just a brief summary of why BGMs are used on some very big and challenging projects. But firstly, we just wanted to say that no geomembrane is suitable for every single application, and we certainly suggest a detailed engineering assessment for each major project. But BGMs do offer a wide range of benefits for many challenging projects, and we always think that they should be one of the geomembrane types considered for each project. BGMs are thermally stable in high heat zones, so they don't suffer from the wrinkles from heat. We can also use BGMs on very steep slopes, much steeper than other types of polymeric membranes. That's because you've got an internal geotextile in there. The BGMs are also very heavy and have very good wind uplift resistance, as well as good puncture resistance. So, and one of the other really interesting advantages is that it has a specific gravity of 1.27. So it's heavier than water and it doesn't float up like other membranes do. Just a bit of a laugh there, but showing you some of the comparison between a polymeric membrane on the lower side of that project, and then the Colotanche BGM on the upper side, which is much steeper and also not having any of the wrinkles like that. This is extremely hot project, 46 degrees Celsius. This is that same project in the Pilbara, very hot conditions, extremely hot and extremely steep. That particular slope is 1.3 horizontal to 1 vertical, so very, very, very steep. In this case, it's a high friction angle variant where you remove a siliconized plastic sheet on the underside, and that sticks to the subgrade, so you can go very, very steep on these type of projects. And this is more than it's probably about 5 years old. Many diffs on this particular project, and working extremely well. This just highlights that the material can take, the self weight of coming down the slope, but it's not that you wouldn't want to ever put a horizontal seam on there. That's definitely where you wouldn't want to have a horizontal seam. But obviously here, all your seams are going vertically, so they are not subjected to any constant stress. Just another interesting example that we're seeing. This is a project, it's been going on for quite a few years. This is right here in Australia. It's got more than 1 million square meters of Colotanche in it. And you can see the steep slopes there. Those are 1.75 horizontal to 1 vertical. You can see the people walking on the slopes. The sanded surface is really good for that. It's a non-slip, and that obviously adds to the safety on the site. In all these cases, all the seams you can see there in the center of the picture there, that's a seam. They're all running straight down the embankment, so they are not under constant tension, even though there's high temperature. Just to show you a few other projects around Australia, on the top left there, you'll see a project in Tasmania. You can see how easy it is for the workers to work on these steep slopes. On the top right, you'll see a project that's in central Queensland. Eric, you said your son was about 2 hours inland from Brisbane. This is about 4 hours inland from Brisbane. Very hot conditions. I've actually been on site there when it was 49 degrees Celsius in a heat wave. And that particular project is working beautifully, still 10 years down the line. And on the bottom, you'll see the Colotanche ES3. These are big stormwater retention ponds. They're working beautifully. The BGM is selected because of its puncture resistance, thermal stability, wind uplift, and high specific gravity. We're going to be talking a lot about seams today, and there's a whole sort of science behind the seams, and it does depend on the sort of the mixture of the bitumen that's in the seam. Obviously, it's not just bitumen in there. There's a whole lot of additives as well, including SBS and some calcium carbonate, which stiffens up the mix. But it all depends on the sort of composition of that. I mean, bitumen is probably 50% of the mix. But it's an important thing, but it's a tried and tested method over many years. So the typical one is a flame torch with a roller, and then you've also got electric welding machines. Both of them are working well, but typically you would like to see some flow of bitumen from the seam to ensure that you've got good coverage across that seam. Just to show you some testing that's been done around the world. We love testing that's been done. Some of it's very favorable to us. Some of it's challenging, so that's fine. We'll take it and we'll improve from that. But you know, some of these tests show the long-term performance of BGMs over 30 years, and obviously testing to other sort of chemicals as well. So there's lots of tests, interface friction tests as well. On the top left, you'll see a little quote from Charles Darwin. It says, "It's not the strongest of the species that survives, nor the most intelligent, but the one that's most responsive to change." And that's what we like to be. We say, like, if we need to adapt, we're happy to do that. And you'll see some of the presentations about seam strength. We've actually got like a lot of solutions, and there are solutions available for that. These were actually presented at the latest Geo ANZ2 in Melbourne a few months ago. But effectively, you can actually strengthen up the seams with mechanical fastening. That's where you're actually bonding the top and bottom layer of the polyester in the seam for mechanical fixation. You can either use like pins or actual fasteners to do that. And then you would cap over it very easily. On the bottom right-hand side, that's a project in Western Australia. You can see like a little capping strip that goes over the seam. Other ways to combat the problem, if you see it as a problem on site, is to obviously reduce the temperature, and you can do that with like aluminium capping strips. And those capping strips reduce the temperature quite considerably, as well as increasing your bond length for tensile strength. You can also use highly reflective paint on the seams if you want to reduce temperature significantly. So there are lots of different ways that you can do that. So in general, you know, BGMs have been used very successfully on lots of challenging projects around the world for more than 30 years. And thank you for your attention.
Thanks, Rob. We'll start off with the first presentation from Eric. So, Eric, all yours.
So, am I sharing the right screen?
Yep.
Okay, very good. Thank you, Rob, for the introduction. So we have a good overview of the different projects, etc. So that's good. So again, I'm doing the first contribution, and Kerry Rowe will do the second contribution. So voilà, that's how we split the work. So why did we work on this study, on BGM seams and seams in general? Lining is only good, as good as it seems. If the seams are failing, the lining is not going to work. So it's really something which has to be understood. But we've been working in the geoscientific industry a lot on polyethylene seams, and I'll come to that after. But in fact, it seems that we maybe have missed in the past working more closely on what's happening with other products. Probably because of the success of BGM, things came to be more attractive. But anyway, that's what we are doing now. So which situation can we have tensile stress in a seam? So in basal liners, one of the obvious one is if you have settlements of the subgrade, this will create an elongation of the liner overall, of the lining, the line, which constitutes the lining. And obviously that will create stress because of the elongation of the liner. You can have settlement of a capping system. If you have settlement, you will have movements of the liner. They're going to move one against the other, and that will create, again, tensile stress somewhere in the structure. Another way to look at it, if you and that will apply on very large surface as well. If you have a very large plane and it is creeping down, I would say, because of different reasons, this displacement in the plane of the liner will, everything is not aligned, so it will create some lateral movement, and that's things which have been observed already. So to go back on what we do, so that's the situation where you can have a stress. It's not specific to bituminous or polyethylene or anything. It's really generic situation where you can have a stress. There are many others. If you have some hydrostatic stress because of gas or whatever on a membrane which is underwater, this gas can create stress as well. So with polyethylene geomembrane, how do we weld the geomembrane? We have to control the temperature, the speed, and the stress which is applied on the two panels together. And doing so, we create a continuous material, which is basically, we are aiming at creating something completely continuous from one layer to the other, going through the weld. So in an ideal world, there would be no change of mechanical property, crystallinity, permeance, etc. It would be a really continuous structure. And if we manage to achieve that, we are getting the best possible assembly of a lining system. So in ASTM again, so I'm the chairman of D35, so I'm totally thrilled to work on these improvements. We had two very important standards that were developed in the last couple of years. One, which is a guidance on how to weld polymeric geomembranes, because we have since a long time, since I think 15 years or something like that, we have, or more than that, we have the GRI GM19, which defines how, the performance requirement for a seam, but we did not have until this year actually, guidance on how to do the seam. So now we have that, and basically it's how to combine heat, pressure, and speed. So the three parameters I mentioned before, how to play with that to try to obtain the best possible seam. And a lot of work is still ongoing. We're contemplating at having more criteria added, but that's for the future. And we have another standard that came out, which is about data recording procedure for welding. So there is a lot of work done on how to seam, how to weld, and how to document the weld. For bituminous geomembrane, so it's a different product. It's been used for a long time, and it's coming, at the end, what's important to realize, it's coming from the roofing industry. Basically, it's bituminous geomembrane are the grandfather of geomembranes. They've been around since a century or a very long time. First, it was build-up roof. That was a traditional solution, which was used in ancient history also to make waterproofing layers. So we were pouring bitumen and layers of fabric to build a roof. Innovation from the 70s, prefabricated bituminous sheet. They were sold in narrow width, 1 meter, and a lot of experience was gained with this narrow width, especially for welding. The technique to weld were refined. So, and it's working in roofs. My roof is bitumen. Half of the roof around me are bitumen. So it's not something which is weird to see. So we have to understand that despite the very high number of weld, because we have basically one seam for each square meter of material or more, because of the width of the rolls, this is working well. So this is an example now, and this technology, which was used for roofing, was extended to geomembranes. And this is an example of a geomembrane, bituminous geomembrane being welded. So you can see again, temperature being controlled, the speed being controlled somehow, and the pressure being controlled. The three parameters are always of importance. You must control the three of them to get a good assembly. Voilà. So again, it's the same thing. We apply some pressure and we bond the panel together. But what makes the real difference between thermoplastic geomembranes and bituminous geomembranes? The bituminous geomembranes is, even if it's assembled, if it's seamed, it will stay a heterogeneous structure. We will always have a layer of bitumen which is connecting mechanically the top and the bottom layer. So that means if we apply a stress across the seam, the strength of the transfer of stress from one side to the other of the seam is going to be through the bitumen layer. And if we look now at the classical theory on viscosity, where the shear stress is connected to, is connecting the viscosity of the bitumen with the distance between the planes and the strain rate, we realize that in fact we can apply the viscosity theory, we could possibly apply the viscosity theory to the BGM seam. So this viscosity is something which has been developed a couple centuries ago. It's really not something new again. We're into well-known science. So what is the viscosity of bitumen and how can it affect the performance of the seam? If we look in the Shell Bitumen Handbook, which is a Bible of bitumen, which is used for pavement construction, for roof, for everything, it's really how to deal with bitumen. We can find in this document a general trend, which is connecting the viscosity of the product with the temperature. So we see here that the relation between the temperature is actually extending across the entire range of service temperature, and that it is relatively linear. Now, what is the limit to that? On the low end, we can have a product that becomes brittle, like a cold bitumen can be brittle like glass, basically, -30, -40, it's going to break, like pretty much all the products, actually. On the high end, when you reach high temperature, like 120 something there, the viscosity becomes so high that, in fact, the bitumen can leak out of the product. So you can see here examples of the bituminous geomembrane that we have tested in this project. At 115, there is nothing happening really. At 120, you can see that the products are starting to separate themselves. And at 125, you can see the bitumen which is starting to leak. So that really reflects how important is the temperature, and voila. So at very low temperature, below zero, below -20, you can have a brittle product. At +125, it's liquid, basically. So what's happening in between is what we have to understand. So what kind of work have we done? The thing that we have worked on was really to confirm that the bituminous geomembrane seams will indeed rely on the viscosity of the bitumen. And second, we wanted to discuss the impact on the performance of a structure. So that's the film that you've seen earlier. That's the sample that we had. So we took this sample and we ran some tests, some tensile tests, D7275, and some seam shear strength tests per ASTM D7056. And we've run these tests at different temperature, and I will show you after why we did that. What did we get in terms of tensile properties? So that's really only the sheet which is exposed to a tensile stress. What we see is that there is about 25% loss in terms of seam strength, of sheet strength, I'm sorry, at 40 degrees Celsius versus the value that we've measured at 23 Celsius. We have lost half of the strength of the sheet at 60 Celsius and 55% at 80 Celsius. And this is all very normal because any product, any polymeric material, we would observe something quite similar at the end with polyethylene, polypropylene, or any other geomembrane. The temperature will affect the sheet strength of the product. Now, if we look at the seams, what we observed, so again, now I'm comparing the retained seam shear strength of the BGM with the sheet strength at the temperature of interest. So in orange here, you can see the sheet, and in blue, it's a seam. You can see a reduction of 32% at 40 Celsius, an additional 32% at 40 Celsius, an additional 72% at 60, and an additional 92% at 80 Celsius. So really, we can see a very steep change of seam strength property. And if we compare it to the initial value, at 40 Celsius, we have lost about half of the, I would say, the design strength of the product, that is the one that we usually consider for the mechanical analysis. and it goes up to 96% at 80 Celsius. So 80 Celsius is pretty on the high end. I'm not sure how often you would see 80 Celsius on a job site, on a black liner, but 60 Celsius is pretty reasonable as an assumption. Exposed to the sun, that's the range of value that we could expect to see somehow. So clearly, at the end, the seam offers much less resistance than the sheet when exposed to a high temperature. And what we found is, in fact, the relation between the seam shear strength versus the temperature is exponential, as you can see here. So we have, when we plot the numbers in a log linear scale, you can see a straight line. So that means there is a logarithmic relation connecting the two products. And we realized that it's in fact exactly the same shape of behavior as we could see as a relation connecting together the viscosity and the temperature per the Shell Bitumen handbook. So this observation, just looking at the shape of the curves, this really supports that the properties of the bitumen is controlling the behavior of the seam, and therefore that the classical equation connecting viscosity with other parameters is in fact controlling the shear strength of the seam. But all these tests that we've done, they were under a fixed strain rate, which is what we do in a tensile tester. We apply a displacement, a crosshead displacement. So it's like we have a fixed strain rate. And if we change the strain rate, we're going to have different numbers of force. And but either way, that's what we have observed. We've modulated the temperature, which affects the viscosity. And we saw that there is a relation which is consistent with this relation here for viscosity, for the seam strength. So in the field, such a strain rate is not something that can happen really. What's happening in the field is a forced elongation, and therefore it's going to be a stress. So the question we had next is, can a constant stress cause the failure of the bitumen, the seam? This can be answered by conducting tests where a constant load is applied on the seam and observing the behavior with creep test. So a creep test is a test where you control the load. You have a constant load, a constant stress, and what we want to see if how this constant stress is going to affect the change of length versus time, which is in fact the speed in that case for this equation here. So we set up a work plan. And so you can see here the orange graph is the tensile properties of the sheet. The blue line here is the seam. So we used a variety of temperatures and percentage of the seam strength. So in dark green, it's 50% down to 10%. And we've looked how would that affect the behavior of the seam. So you can see here the environmental chamber. It's a closed loop system to control the stress. And we get the numbers, and that's the kind of results we get. So here, an example with a test temperature of 40 Celsius, we wanted to apply 30% of the sheet strength, of the seam strength actually, that's the sheet strength. So from initial value force of the sheet at 23 Celsius of 21.9 kilonewton per meter, so that's the design value we would normally consider for the sheet. We reduce it to reflect the temperature of 40 Celsius. So we are down to 16.7. That's test data. Then the seam strength that we get at that temperature is in fact limited to only 11.3 kilonewton per meter. So we apply 30% of this value, which gets us down to 3.37. So it's much lower than the initial value, but that still reflects the test condition that we've decided here. And what do we get? A displacement rate that we can measure here, that's the slope of this curve, and a failure time, which is the time at which we have no continuity left. So the two panels have split apart, they're no longer connected together. We tested all these conditions that I've shown you, and we got this cloud of data. I would say the numerous data connecting together the temperature with a rate of displacement, with a variety of percentage of the seam strength. And we confirm that, again, there is this relation connecting together the speed of displacement, rate of displacement, so the U value in my viscosity equation, with the temperature for a variety of stress. So this really confirms that these equations does control the behavior of the seam. We looked at the time to creep failure under the various shear stress, and we found that first, the time to failure were very short. So the green curve you have on top here is 10% of the shear strength of the seam at the test temperature. So that can be here, as I showed you before, it's already about 15% of the sheet strength. So we are very, very low. And we see that the failure times are pretty much very, very low. They are in days, if not hours, if not minutes. So using the trends observed, what we observed is that with a stress as little as 10% of the short-term strength, it just takes a few days at room temperature to break. And that to me was very interesting because I was working on this project since a couple of months, and eventually I found this paper by Kerry Rowe and his student, Mr. Francie, which they use a completely different approach, and they published this paper in May 24. So that was just a few months ago. And they published this document, this graph, which is connecting the failure time with a percentage of the tensile strength. And it's funny to see that they are also observing failure times in days for a percentage of the shear strength, which is between 10 and 20%, say. And this is completely consistent with what we have observed. So it was really, despite we did not use the same approach, we landed pretty much in the same ballpark. So that to me was very, very interesting in terms of reliability of our studies. So in terms of what can we get out of this? So the existence of a relation between the failure time, it basically, from an engineering perspective as a geotechnical engineer, it raises questions regarding the reliability of bituminous membrane when they are exposed to stress under any temperature, because we can see that there is a relation between the temperature and the failure time, but viscosity goes down to much lower temperature. So if there is a failure, it's going to be within hours or days. Now, what can we learn from the roofing industry? Because as I said before, in the roofing industry, they have no problem. They've been using these products since many, many years. What makes the big difference? First, a very important aspect, roofing products are using two layers. They have two layers welded one on top of the other, a base sheet and a cap sheet. And the base sheet is attached to the roof deck with mechanical attachment or full surface adhesion. And then the cap sheet is bonded after. So the joints are always covered by another panels, first thing first. And I give you here the link to look at this information if you're interested. Second aspect, which is very important, the membranes are always installed on a rigid, solid deck. Usually it's going to be plywood or insulation material. It is a very rigid, stiff deck. It is not soil. Third aspect, low slope. The building code of Canada forbids, and Canada is not Australia, it's much colder, but we have hot summer. It forbids installation with slopes more than 1 to 4. So that's based on the experience, that's a code thing, and it's well accepted in the industry. So if we compare really the structure of the roof and bituminous membranes, that's really the difference. The base sheet on a roof is attached mechanically or by different systems to a deck. And then we have a second layer, which is coming on top. In the case of a bituminous membrane, we have a single seam, to which we entirely rely for the waterproofing. It's a big difference. Conclusions, and I know I need to be quick. The short-term seam strength of bituminous membrane is highly sensitive to temperature. The bituminous geomembrane seams do exhibit a viscous behavior. And the main consequence for that is that if a seam is exposed to a constant stress, it will fail eventually. It must not be exposed to a constant stress because of the physics of the material. Impact on the design, the reliability of a seam will depend on the risk of developing stress. If you have a deck there is no problem. There is a long history of success on which you can piggyback. If you install the bituminous membrane on a concrete deck, the seams are not going to move. But if the substrate is likely to settle, if there is likely to be some settlements or movements or tensile stress developing, then this deck is not there anymore, and stress and therefore failure can happen. And with that, one of the recommendations I came up, that's probably my ASTM hat which is speaking, welding should probably not be used for bituminous geomembrane, because welding refers to a complete set of concepts which are not met here. Sealing would be a much better solution. Sealing, bitumen is a fantastic sealant. It's used in many industries for sealing. And indeed, on the seams, we should consider that they are sealed, not welded. So that's really my contribution for today. And I will leave it to Kerry to provide us with more information and more research.
Thanks, Eric.
And questions are going to be at the end of the presentation.
Yep. So we'll pass the presentation to Kerry. Kerry, you're on mute.
You see my screen?
No, not yet. It's not coming up.
Not coming up. Okay, let's try this.
Right, it's coming up. It's we are not seeing the presentation part. We are seeing the PowerPoint. Yeah.
You're seeing the proper PowerPoint?
Yep.
Okay, I'm just going to fiddle with another little thing here, and I'm ready to go. So we independently from Eric have been looking at the same issue.
Kerry, sorry, sorry to interrupt. We are seeing your slides, but not the PowerPoint presentations. Yeah.
Oh, okay. I have to go back and reshare.
Yeah.
Let's see here. Stop sharing. Okay. Now are you seeing my screen?
Yep, that's
All good?
much better. Yep.
Okay. So I wasn't lying in bed dreaming one night that I needed to look at geomembrane seams. We had a number of consultants come up to us and say, we're having problems. We don't have much science behind this. We're being asked to use them by our clients, and we're being told to take responsibility. So can you get some science? And that's really what launched us into studying BGMs. So we're talking in particular today about the seams. And here's a photograph in the field of a problem with seams. And as Eric pointed out, even though we should never be designing any geomembrane for sustaining tension, we can't avoid the fact there's going to be some tension. There's going to be tension if you've got some undulations and you've got water pressure acting on it. You've got down drag when you've got a waste that's consolidating like tailings. You can get water and gas pressures underneath it, differential settlement, melting of ice. Is not perhaps too much of a problem in Australia, but melting of permafrost is a big issue in Canada. If you've got a stiff protrusion and soft materials around it, or even just simple little ruts that are in the subgrade and you bridge over it, all going to induce tension, which will be particularly problematic if you've got a weld going across it. That is true irrespective of the material, because welds are the weak point. Now, we have two papers. Eric referred to one of them with Francie, and we have another one that's come out recently with FAN. This is one of the first things we did, very simple. We took a BGM that was welded, we painted some white horizontal lines across the weld, and we subjected it to a sustained tension. And with that, we began our monitoring, and we saw after a short time, those white lines were no longer horizontal, and it was starting to open up at the bottom. Longer, the lines aren't even connected anymore, and it's opening more. And a little time later, it fails. Same story that you just heard about from Eric. So let's quantify this, and we took a different approach, but nevertheless came back with the same or very similar results. We tested 2 different BGMs from 2 different manufacturers, and we subject them to a constant stress as a proportion of the sheet stress. And all of these welds were within 10% of the sheet strength. Many of them were as good as the sheet strength in a short-term test. And so they were good welds that we started with. We did do some tests on not such good welds, and it really didn't make much difference. So here you see the data for 2 different BGMs from 2 different manufacturers correlating very well. And you see that if we go to 30% of the strength of the material, it failed in 0.1 of a day. Now, why did we pick 30%? Because we all know that HDPE suffers from stress cracking. And the stress crack test is done at 30% of the yield strength. And we have done quite a lot of tests on welds and found that the welds typically crack, depending on the material, depending on the quality of the weld, between 1 and 30,000 hours for a good HDPE weld. At 50 degrees C in a surfactant solution. So we're doing the same procedure, it's just on a weld, not the sheet, that we do for a stress crack test, but without any notching. And this compares with about 3 hours at room temperature for the BGM. Quite a difference between 3 and 1,000, let alone 3,000. Now, if you go to a lower stress, as you might expect, it takes longer, but not all that much longer. So if we go to 10%, it's about 128 hours. Now, another way of looking at it is what is the relationship between strain at rupture and the stress that's applied? And you can see that if we only have 5% of the strength, we're still failing, but at a quite small 4% strain. The higher the load, the more it strains. And that's because the higher load gives you more creep. And eventually it fails in a brittle manner, but it is creeping for much of that time. So those are all in isolation. So we thought, let's try simulating what may happen in the field. We've got a indentation 75 millimeters deep, 150 millimeters wide at the bottom. It's in a sand. We put a BGM with a weld on top of it. We put a geotextile, we put some sand on top of that, then a geotextile, then some gravel. And we can apply loads. We can also apply water pressures in our geosynthetic liner longevity simulators. So here's what it looks like within the cell. And you can see the indentation is 600 millimeters long. And we started pretty carefully at a low stress, 20 kilopascals, so about 1.2 meters of cover soil in terms of the weight that was acting on it. And we applied a water pressure as if the water was at the top of the sand. So about 12 kilopascals or 1.2 meters of head. And in this case, it sat there. It didn't leak for about 24, 25 days. And then it suddenly started to fail. And within about 2 days, it had gone up from basically zero leakage to 200 litres per day per metre of head. That's for a 600 millimetre long divot. And in fact, the opening up was 500 millimetres long, as you'll see in a moment. But just to recap, 20 kilopascals of applied pressure, that's where it ruptured. 200 litres per day per metre under 1.2 meters of head, not a large head. And this is turning the seam upside down, so you're viewing it from the underside, and the rupture length was about 500 millimeters. So it obviously began at one location and then propagated, is what you infer from looking at the rate of increase in the leakage. Here is results from another test, and we started at 30 kilopascals. We sat there for a few days, 4 to be precise. Then we increased it fairly quickly up to 50 kilopascals, and we let the load sit there. And in fact, almost immediately, 0.04 of a day, after increasing it from 40 to 50 kilopascals, we saw a failure. And the leakage began at about 200 litres per day per metre and increased with time. When we decided to terminate the test after about 46 days, it was about 525 litres per day per metre of head. And this was under 1.9 metres a head, 19 kilopascals in round numbers. So here is a roll of BGM. And what I did for this table is I went to the literature and I pulled out the data sheet for a commonly used HDPE and one for a BGM. It was a 2 millimeter HDPE and a mass of about 1.9 kilograms per square meter, a roll width of 8 meters, a roll length of 105 meters, and it's pretty simple math to calculate. That means you'll have about 1,500 meters of seam per hectare, just considering the ends and the edges of the rolls being seamed. And that's without any additional patches being considered. We do the same thing for the BGM. Its thickness was 4.8 millimeters, and as you've heard, they are substantially thicker and heavier at 5.8 kilograms per meter squared. The roll was 5 meters wide, 64 meters long, and that gives us 2,300 meters per hectare, or about 50% more welded. So 50% more welded distance with the BGM that I picked for this particular example and the HDP I picked for this example. So let's carry this one step further and we'll look at the time to rupture at 30% yield. And for the HDPE, it took 125 days. For the BGM, it took 0.01 days. So there's a 1,250-fold difference. There's also a big difference in temperature, but we'll come back to that later. Next, let's look at leakage. And so we've done the same types of GLS with geomembranes, with welds that are defective on geomembranes that are HDPE. We've done them on BGMs without defective welds and with not 100% welds in the 80 to 90% range. And we have, and the extreme case we've looked at for polyethylene is just wasn't welded at all. And so we can compare the leakages on as similar as cases as we've got. We don't compare the same cases because we just didn't have the data. This wasn't done for comparative purposes, but if we look at the HDPE, we're dealing with much higher stresses. We applied 300 kilopascals, and our leakage in terms of litres per day per metre of seam that's failed or was never proper in the first place, per metre of head. So we take the leakage, we divide it by the number of days to get a rate, we divide it by the length of the defect, and we divide it by the head. And that gives us 0.2. If we now look at the BGM, we only tested at 20 kPa. I said these are not apples and apples comparisons, but our leakage is 330 or 1650 times higher. We go to 500 kPa. In our HDPE case, our ratio is 0.23. We go to 50 kPa, it's 830 for the BGM as our leakage. In normalized terms, a 3,600-fold difference. Now, I'm going to finish off by putting this in context. If we have a composite liner in a landfill, we know from double-line landfills, and this data you see here, that if we have an electrical leak location survey, the leakage is typically less than 250 litres per hectare per day. Now, I'm just giving you that as a benchmark. I'm now going to be talking in litres per hectare per day. So we go with our 2 millimetre HDPE, and we assume 5 metres ahead. It's in a pond or something. And we assume that 1% of the seams fail. Now, we don't expect all the seams to fail. 1% is not a very large number. And we get a leakage of 17 litres per hectare per day. If I do the same thing with the BGM, using the same data set we saw before, it's 95,000 litres per hectare per day. Now, you could say that's a bit unfair because 1% of 1,500 is less than 1% of 2,300. So let's compare them for 15 metres each. And you see 17, of course, for the HDPE and 62,000 for a BGM. Now, the point I want you to recognize is in a dam or a freshwater reservoir, nobody'd be worrying about 95,000 litres per hectare per day. You wouldn't notice it. It's no more than the evaporation. You certainly wouldn't notice 62,000. It really doesn't matter. But if you're trying to contain a contaminated liquid, that becomes a rather different story. So let's wrap this up. Geomembranes don't like to sustain tension, no matter what it is. HDPE seams will fail in 140 to 125 days, depending on the quality of the seam, at 30% of the yield, at 50 degrees C in a surfactant. And we typically want those seams, in fact, the sheet, to be less than 6% strain. BGMs fail at 0.1 day at room temperature in air. Now, remember, Eric showed a dramatic drop as the temperature goes up from room temperature to 50 degrees. So this is being very generous, relatively speaking, to the BGM. At 3% strain, we got breaks in about 1 year projected from the curve I saw. We've never seen one at that strain for an HDPE seam. We've been doing tests for years now. We're expecting it's going to be probably after I'm no longer with us. So BGMC can be very effective. You heard at the beginning, they've been used on lots of applications, particularly when you're not too worried about 10 to 100,000 litres per hectare per day, which is your typical reservoir freshwater. application. You've heard that they're easier to seam. You've heard that they don't stress crack and they don't wrinkle, and they're all true. But it's only part of the story. Whatever the material is, whether it's PVC, HDPE, LLDPE, BGMs, or whatever else you want to talk about, you've got to look at what the potential failure modes are, what's the allowable leakage, and what's the service life when you're designing. And take all of those factors into consideration. And we should be designing on facts, not wishful thinking. Luck is fickle. So, great for water, but carefully consider if you're going to be containing any fluid where a leakage of 10,000 litres per day is high. Acknowledgements, the funding from Canadian government, from some consultants and a contractor, and my colleagues, and the two people who did all the work, Dr. Fan and Dr. Fancy. Thank you.
Thank you, Kerry, for the presentation. If you have any questions, please do type it in the Q&A. There are a couple of questions here that I think we can address while we are online. There's still a few more minutes until the end of the webinar. Okay, let me read out the questions. So the first one would be, is there a reason why HDPE liners are not being used in roofing industry if the weld joint are high in mechanical properties compared to BGMs?
They are used in the roofing industry. It's called TPO. It's broadly used. It's one of the lining material which has the biggest growth in the roofing industry. This and PVC. In fact, in hot weather, if you're thinking in North America, if you're thinking of the south and the west of the US, I doubt there are still bituminous membrane installed, at least not exposed. What they do sometimes is an inverted roof where you have the liner which is covered by concrete tiles. And in those applications, sometimes people are still using bituminous, but the exposed roof is really TPO, so which is polyethylene basically, and PVC, which are taking the vast majority of the market, the biggest growth.
Well, thanks, Eric. The second question would be, would the 200 mm weld strip be able to absorb certain settlement on the substrate, and it allows for the BGM to elongate and adapt to the sediment shape?
We'll leave Kerry answer that.
I understand the question. Could you read it slowly for me?
Yep. So the question is, would the 200 millimeters weld strip be able to absorb certain settlement on the substrate and allows for the BGM to elongate and adapt to the sediment shape?
Probably some, but the fact that it's adapting means it's going into tension to adapt. There will be some creep, but remember we've got the reinforcing there that you heard Rob talk about, and the seam, at least the ones we're talking about, are bitumen to bitumen seams. Rob did talk about textile to textile seams. That's a little different. But the bitumen to bitumen seams, if you've got an indentation and you've got an applied stress that's going to be maintained, for example, a cover soil or water, then I think you've got some potential problems.
Thanks.
Sue, just to answer that, can you hear me? Can I just put a few comments on there? The question was like regarding the 200 millimeter capping strip. You can actually make that capping strip as wide as you want. 200 mils is quite a standard one, but you can actually make a 500 mil capping strip, or you could make a 1 meter wide capping strip. So that would give you a huge, big, wide sort of variance to accommodate some extra sort of extension in the subgrade. As Kerry was saying, those 75 mil gaps underneath the weld are quite extreme. I mean, even though you can take some movement in your subgrade, those are quite unusual ones, but if you had a 1 meter wide capping strip, for sure, that would be able to accommodate through that.
How do you weld for 1 meter? You have 2 torches?
You could do it. I mean, like you do, like with a normal roofing membrane, you torch right the way across the whole seam. You know how you torch a 1 meter wide membrane on a roof.
Okay.
The same principle.
On the roof, you unroll the product as you torch
Yes.
it. So that's,
Yes.
I don't see how you're going to do it when it's the other direction, because it's the width,
When
the length of the roll.
We're talking about a capping strip that goes over the top. So you do your normal weld, 200 millimeters overlap.
Oh, okay, got it.
And then so I'm talking about the normal 200 mil overlap, which you just go in the gap, and then you torch on a big wide capping strip. Additional capping strip on top. It can be 200 millimeters wide, but it can be 500 mils. It can be 1 meter wide if you're expecting a lot of movement. So that's an additional.
You're replicating what they do in roofing at the end.
Roofing, exactly right. So
layers.
So you're getting like a whole big chunk of extra bond length in there.
Right. Thanks, Rob. Yeah. Maybe one more question before we end, because I see that's one interesting one. So the question is, as shown in the intro, some BGM sticks to the subgrade on the slopes. So would there be similar implication in terms of the loss of BGM shear strength against the soil at higher temperature here?
If I can speak first, I'm happy to go there. What I've presented is that, in fact, what's controlling the behavior of the interface is the properties of the bitumen. So indeed, when you heat the structure, you reduce the viscosity, you reduce the viscosity of the bitumen, and therefore the shear strength property, the adhesion property, will change. So I think there was some data published on shear strength at high temperature. I have that in mind, but maybe it's something which is in project.
And sorry, you Eric. I was just going to say something when you finished.
And so there is a loss. I was actually speaking today with one of my colleagues from the Building Code of Canada, and I was asking him, do you have data supporting the 4:1 maximum slope? And I hope to get them eventually, but there are some data supporting that the 4:1 slope is the maximum accepted slope on roof in Canada, and that's only for bituminous membrane. It's not for TPO, PVC, EPDM.
Yes, Rob.
So yeah, just to answer that question a little bit more on the interface friction at higher heat, you would expect it to be lower as you go higher. It's the same as what Eric is saying there. But just to bear in mind that you can actually adjust the viscosity of the bitumen in the mix by like a lot of different ways. One of the things is adjusting the amount of SBS in there. The more SBS, the more viscous it is. As well as the amount of calcium carbonate. That's like a viscosity enhancer. So typically in the bitumen blend, you've only got 50% bitumen. The rest is additives. So it does, if you have a very sort of steep application and you want to enhance your shear strength on that, you stiffen up the bitumen mix with those other additives, and that enhances it. And we actually do that. We make different types for like extreme conditions.
Can I ask a question?
Yes,
this
sure.
is a question.
Is this for me or for everybody else?
It's for you. It's
yes,
for
sure.
you. When you find a solution to a problem, I then ask, what are the unintended consequences? What are you sacrificing for that solution?
Are you talking about when you're making it more viscous? It's the one thing that you have to be is always the balance is during production. You have to have a certain amount of viscosity to make it flow during the production process. So you can't have it to being too stiff, but you want the good balance between what's workable on site and giving you good performance versus what physically can be actually manufactured.
Isn't it APP?
Any
which
other
is used?
effects on long-term performance or anything like that? This is an honest question. I don't know.
No,
the answer to it.
it's good that you're asking. I mean, and typically you've the amount that the bitumen that's in there. I mean, on a Kerry, you mentioned a 4.8 mil thick membrane, but we also make 5.6, and we also make 2.2 mils, which have, by the way, very similar surface areas to the HDPE membrane that you mentioned. So those come in 140 meter long rolls by 5.1 meters wide. So that changes those ratios that you had there. But effectively, the bitumen is providing you with the waterproofing, and there's enough thickness in there to, obviously it's giving you the very low permeabilities. And we see whether you take a 2.2 millimeter thick BGM or a 5.6 millimeter BGM, you're still getting the permeabilities sort of in the range of 6 times 10 to the minus 14 meters per second. So the amount of you can have less bitumen but still have the very low permeability, and that's the main criteria that you're looking for. The rest of the mechanical properties are coming from the polyester reinforcement that's in the center. So it just for interest, I mean, we're talking about different types of the actual materials that are used in the reinforcement affects the seam strength. Actually, the standard BGM will have polyester nonwoven, needle punched, and with a glass fiber reinforcement. But you also we have the thermally bonded versions with the glass fiber inside it, and those actually have higher weld strength. So if you're looking for higher weld strength, there are those sort of options as well. But on the very high temperatures and high constant load, you have to go for one of those other 3 areas which I mentioned: the mechanical fastening, or the capping strips, or the heat reduction paints.
Right. All right. Thanks, Rob, for answering the question. We are 7 minutes late, so I think we have a few more questions, but I'll send it over to all the panelists so that they can come back to you with an answer.
Stu, can I just say one thing? Just want to, from the Australasian chapter of the ACIGS, want to congratulate Kerry for being awarded the Gerald Hertzberg Canada Gold Medal for Science and Engineering. Fantastic achievement, and I think testament to the very long involvement and work that you have done. So just wanted to squeeze that in.
Congratulations.
And it is not an award which is within our industry. It speaks to the other people, to the people we want to reach, because that's the most important in my eyes.
Yeah, right. I mean,
everybody knows Kerry. Everyone knows he's the best with our group, but now they know as well.
Now others know as well.
I mean, thanks, Eric and Kerry, for your time. I know it's late there. I mean, thank you for your contribution, and Rob, thanks for your time as well, and also sponsoring the webinar. We'll end the webinar here. There will be a recording, and yep, see you guys next year. All right, have a good year.
Thank you very much, Kerry and Eric, and thank you, Sue.
Bye, everyone. Bye. Yeah.
Thank you.